What is multiple regression? Some time ago, we discussed simple correlation and regression for just two variables. And I hope that you remember something about these regression coefficients and what is the difference between unstandardized and standardized regression coefficient. So multiple regression is basically the same thing. Only instead of one predictor, we now have two predictors. Two independent variables, we call them predictors, that we want to use in order to predict some outcome variable. And this outcome variable is also called dependent variable or criterion variable, but it's the same thing. It's basically dependent variable, the variable that we are trying to explain. And what are we doing here? It's easier to represent this graphically. Our dependent variable has some kind of variance, and its variance is comprised of error or some kind of sources of individual differences that we don't know, and it also is comprised of the effects of these two predictors. So what we are trying to do in regression is we are trying to take all this variance of our dependent variable and separate it into portions. The portion that is associated with each of these individual predictors, with each of these independent variables, and the rest of the dependent variable variance. And the rest of the variance, it might be predicted by some other causes. We don't know what explains it, so we call it error variance. Error variance or residual variance, it's basically unexplained variance. We don't have any other basis to explain it. And essentially, imagine that this dependent variable variance is like a pie. So we are trying to separate this pie into two slices for two predictors, and the part that no one has claimed, the part that is not going to be eaten by any predictors, so it is a residual part of the pie. And this metaphor is very useful because it helps us to remember that two people cannot eat the same slice of a pie. So essentially, every slice of a pie goes to a different predictor. But if both predictors claim the same slice of this pie, no one gets it. To illustrate it further, we can take a look at these diagrams from the textbook of Tabachnik and Fiedel, a wonderful textbook on multivariate statistics. And basically, why do we even have this problem of shared variance? Because the variance that two predictors share with a criterion-dependent variable, they may share with each other to a different extent. And when we are trying to separate this variance, we are trying to exclude this common portion. And we will see very soon how it happens. So just to give you an idea of how you calculate regression, in SPSS you go to Analyze Regression Linear, and there in the menu you basically put your dependent variable, your predictors, and there is in principle nothing else that you need. So running a regression is quite straightforward. It's much easier to run it than to understand what comes out. So to illustrate this approach, let's take a look at this example. I've included into my regression model the data that I was just talking about, where we have grade and two predictors, self-esteem and optimism. So as a result, in our regression model, we have, first of all, an estimate of R squared, which is basically how much variance of our dependent variable do all the independent variables, do all the predictors explain together. And this part includes all the variance that is shared with any of the predictors by the dependent variable. And here we see that about 8% of variance in school achievement is explained by these two psychological characteristics. And if we make an adjustment for the number of variables, it is even a bit smaller. But normally we just report unadjusted R-square unless there are very many variables. So 8%, is it much or is it little? Well, it depends. Because of course school achievement depends on so many things, from a child's IQ to socioeconomic status of the parents, etc. So many things that predict school achievement. So if we have predicted even 8% with our two psychological variables, maybe it's not such a bad result. Then the second table, which is given to us by SPSS, is called ANOVA table. A bit misleadingly, because, oh, we are running regression, why is the table called ANOVA? Well, because regression is based on the same Fisher's statistic. So essentially, regression and ANOVA are like two parts of the same general linear model, that they are very closely interconnected. So to evaluate the significance of a regression, we use Fisher's F-test. And this table tells us if this R-squared that we have seen in the previous table differs statistically from 0. Is this R-squared statistically significant? Does our model explain anything at all? And as you can see here, the estimate of significance is pretty good. It's less than 0.001. SPSS gives us a little misleadingly 0.000, but please never publish in your research reports that your significance equals 0, because it's theoretically impossible. Your significance is always non-zero. So if you see in SPSS, like here, 0, you just put p less than 0.001. And the most important table that we are looking for in regression analysis is called coefficients. So here, for every variable, we have coefficients, unstandardized regression coefficients and standardized regression coefficients. And for every regression coefficient, we have an estimate of statistical significance, which basically tests the hypothesis whether this regression coefficient is different from 0, and what is the chance to get this difference from 0 by chance alone. So as we can see, for optimistic attribution of successes, the level of significance is pretty good. It's 0.003, so it's less than 1 in 100 chance of getting this effect by chance alone. But for self-esteem, this level of significance is 0.093, so essentially it's not significant, and probably we would want to exclude this predictor from our regression model. So what do these coefficients mean? If you remember a little bit from our discussion of simple linear regression, where we just had two variables, B coefficient was basically the number that we included into the equation of a line that describes the relationship between y variable and x variable. So B is basically a slope of the line that links predictor to criterion. And an interpretation of B coefficient is by how many points would the dependent variable change if this predictor changes by 1 point, and if all the other predictors in the model are held constant. We can say controlled for. So depending on what scale your variable is measured in, this B will take completely different values. So here, for example, this B coefficient for optimistic attribution of successes is like 0.03, because it's a fairly large scale, and for self-esteem it's 0.06 because it's a smaller scale, it has fewer questions. But why is it so small, B coefficient? Well, because the outcome variable is measured on a very small scale. The school grade goes only from 2 to 5 in Russia. So essentially, these B coefficients are not very helpful to us. Of course, in sciences where this measurement scale has some objective nature, where it is important for some reason, it's like a common scale. In physics, for example, people publish those raw unstandardized regression equations. And these B coefficients are basically the numbers that you need to include in your equation in order to predict the actual school grade by substituting a questionnaire score for optimism and a questionnaire score for self-esteem for this child. And then after you multiply this score for optimism by 0.032 and you multiply this self-esteem by 0.066, you need to add a constant which is called intercept, which is basically the value of our dependent variable when all predictors are 0. So essentially it's a constant that we need to add to this. Why is this constant 10? Well, because it's meaningless, because this value is out of range. A school mark cannot, of course, be 10, but also the values, the scores on these two questionnaires can never be 0. These were average scores, so they were like maybe 40 or something for self-esteem and probably 60 or 80 for optimism. So it's theoretically impossible to have a questionnaire score of 0. That's why this intercept is so large. Basically, it doesn't make any sense. It's not useful at all. And of course, in the actual data, we also have a contribution of random error, which is this little Greek letter epsilon. And we can, this standard error basically describes the standard deviation of this error, which on average it's supposed to be 0. And from person to person, the standard deviation is 1.23. So if you want to simulate the actual data, you always need to remember to add some random error. Otherwise, your data will look artificially perfect. But these unstandardized coefficients are not so useful for us. What we are interested in are mainly standardized coefficients or beta coefficients, because these are essentially effect sizes for each individual predictor and they are not dependent on scale. So regardless of how many questions there are in my questionnaire, the beta coefficient is supposed to still remain the same. And it is interpreted as change of dependent variable in standard deviation units that is associated with one standard deviation unit change in my predictor if all the other predictors are held constant. So, for example, what will happen if optimism increases by one standard deviation? And I just look at this beta coefficient here and I see that the school grade will increase by 0.22 standard deviations. And from my descriptive statistics, I know how much it is, so I can kind of propose a substantive interpretation to people. Sometimes you want to propose this interpretation in terms of raw scores, sometimes in terms of standardized scores. So it depends. But if you compare results of different studies, you definitely need to have standardized coefficients. That's why normally when we publish mainly standardized coefficients only. And if you remember from our discussion of correlation and simple bivariate regression, the correlation coefficient, Pearson correlation, was the same as beta coefficient when we just had one predictor. However, when we have two predictors, there is a difference between the beta coefficient and Pearson R. If you remember from the beginning of these slides, the correlation between self-esteem and school achievement was 0.18, and it was statistically significant. But the beta coefficient that we see here in the table is only 0.12, and it's not statistically significant. Why? And the answer is very simple, because in correlation, every predictor has its own pie of dependent variable to eat. So basically they can eat as much as their shared variance allows them. However, when two predictors are entered into the model together, we are trying to separate the shared variance of dependent variable into portions that are uniquely shared by each predictor and are not shared by any other predictors. So imagine that we have a dependent variable and 3 different predictors, IV2, IV1, IV2, and IV3. So in a multiple regression, IV1 will get this portion A, IV2 will only get portion C, which it shares with the dependent variable, but it does not share with IV1 or IV3. And IV3 will only get the portion AE. What about the portions that are B and D that are shared by 2 predictors? Basically, they will contribute to R squared. So R squared will be based on all this part of dependent variable, on all this portion of dependent variable that is shared with any number of predictors. However, the beta coefficient for each individual predictor will only be based on the portion of variance that only this predictor claims and that is not shared with any other predictor. So basically, because self-esteem and optimism are also correlated, they share quite some variance. And the variance that is shared by self-esteem with school achievement is also largely the same variance that is shared by optimism with school achievement. That's why the remaining portion of the variance of self-esteem, which is quantified with a beta coefficient of 0.12, is fairly small, and we cannot be confident that it's not zero. So from this, basically you can easily remember it. 2 people cannot eat the same slice of a pie. Each predictor only gets its unique variance. And the consequence of this, the more predictors you have in your model, and the more variance they share with one another, so essentially the higher are the correlations between your predictors, the less there is a chance that each predictor will get a significantly large unique slice of this variance pie. Because if their shared variance overlaps a lot, there is very little unique variance left. And that's the reason why it's a very bad idea to include into regression variables that are very strongly correlated. Usually, adding more predictors reduces the beta coefficients for all the other predictors in the model. However, occasionally you might see a very rare case. This case is called suppression. It's a situation when you have a variable, you add it into the model, it does not serve as a significant predictor of the dependent variable, but when you add it into the model, the contribution of other predictors increases. And this is a very rare case. You may encounter it occasionally. It's a bit hard to explain it in general, but usually the reason is that there are more complex associations between those predictors. They are not independent causes, but they are also dependent on one another. That's why when you see suppression, you can ask a question, maybe a more complex model is needed here than just a simple multiple regression. If you want to understand a little bit more about suppression, there is a nice chapter in Tabachnik and Fiedel. And let's explore a little bit multiple regression. So what are the variables that multiple regression deals with? We assume that our independent variables and our dependent variable are all measured on an interval scale. If you have ordinal variables, it's a bit problematic. If the distribution is close to normal, you can use them in regression. However, if the distribution is not normal, or the number of categories on this ordinal scale is very small, then it's best not to use them in regression and use either a separate type of regression, which is called optimal scaling, or recode them as if they were nominal variables. And as for nominal variables, You can use them in regression, surprise, surprise. But in order to do it, you need to code them. You need to convert them to a special type of variables that are called dummy variables that we'll explore today. And dependent variable is normally interval and normally distributed. Of course, occasionally we might have situations where we want to predict a nominal variable, for example, or an ordinal variable. In this case, you need special types of regression. For binary variables, there is a special type of regression. For nominal variables, there is a special type of regression which is called logistic regression, which is also available in SPSS. And for ordinal variables, you can use some package like M+ or R. So our task when we apply multiple regression is to find the equation that links our dependent variable to our predictors. And we want to evaluate how confident we are going to be in those predictions. What kind of research questions do we ask when we deal with regression? We can ask the question, for example, how well can this bunch of predictors predict this outcome? Or which of these predictors is more important to predict this outcome? For example, is it optimism or self-esteem that is more important to predict academic achievement of children? Sometimes we want to compare regression models with different sets of predictors. For example, we want to add an additional independent variable to see if adding it improves prediction. Another a bit tricky type of research question concerns curvilinear associations. For example, of course you say, but how can this be possible, because regression is linear? But in principle, you can also use linear regression to explore curvilinear associations. You can also use it to study interaction effects between your independent variables. You can use it to compare different sets of predictors. And sometimes you also want to use your regression model to predict new data coming from a new sample. Sometimes we do it in practice. For example, we say we train a regression model based on some sample, and then we deploy it, we use it in a certain situation. Or sometimes we develop a regression model based on one sample that we call a training sample, and then to see how well our regression model can replicate, we use a separate portion of the sample that we call a test sample, where we test it. Because when we evaluate a regression model, it is adjusted not only to our general population, but it's basically adjusted to a specific sample. And there is, of course, sample bias, as you well know. So your regression model may reflect specific characteristics of your sample. And in order to rule out this possibility, sometimes we need a new sample to test it in a new sample. What are the assumptions of multiple regression? Well, first of all, normal distributions on predictors and the dependent variable, then absence of variables that are redundant. So multilinearity is a situation when you have a variable that is basically redundant given the other predictors, or it very strongly correlates with some other predictors. And this is a bad situation because this variable is not going to have a sufficiently large portion of unique variance, and this will make your regression model unstable. That's why it makes sense to exclude such variables. And an even worse case is called singularity, when in your regression you include the same variance twice. Some people who don't know how regression works, or in other statistical models, the same goes for factor analysis, for example, they include into regression a subscale from a questionnaire and a total score that is basically a sum of different subscales. So essentially, the same variance is included twice into the model. And of course, as a result, SPSS probably is not going to estimate this model. So the solution is to exclude either the individual subscales or exclude the total score. So you can use either one or the other, but not all of them at the same time. Some assumptions of regression also concern residuals. So these errors that are left after we have explained some portion of variance, they are supposed to be normally distributed. They are supposed to be linearly related to your variable score, and the distribution is supposed to have the same shape across all the range of dependent variable. This is called homoscedasticity. And another assumption of multiple regression is independence of errors. Your residuals are supposed to be independent, and basically the observations that you use in your model are supposed to be independent. So for example, each row in your data matrix is an individual, and those individuals are all different. There is no data coming twice from the same individual, for example. If you have this association, this is a violation of independence of errors, and you need a stronger, a little bit more complex linear model, which I will discuss also today. So the distribution of residuals, normality, linearity, and heteroscedasticity or homoscedasticity, you can evaluate very simply just by looking at those little graphs. In SPSS, you can ask in the plots section to plot on the x-axis your predicted variable, standardized for simplicity, and on the vertical axis, you're supposed to plot the residual. So if all the assumptions are met, you're going to see a picture like here is shown in the part A, when they are kind of normally distributed if we look from the side at this distribution, and it's uniform across all the values of your predicted variable. If this distribution of errors is not normal, you will see that it's not symmetrical. So this side is smaller, this side is larger. It is asymmetrical, it is skewed. Or the residuals might be non-linearly related to our predicted variable. The error of prediction is larger or more positive in the center, and the error of prediction is smaller or negative on the sides. And this suggests that probably the association is nonlinear and you need to have some more complex model to model it. And heteroscedasticity, also it might suggest a problem with some distributions, or it might suggest that the association is nonlinear. So if we look at our plot produced by SPSS of prediction of grade, on the horizontal axis we have predicted grade, and on the vertical axis we have residuals. You can see that it's not actually not so perfect. It is a little bit heteroscedastic, and that makes sense because the school grades, it's not interval scale, and even if we average 4 of them, still the distribution is not perfectly normal. And for children who get lower grades, we might get a larger error of prediction, etc. For children who get higher grades, we get a smaller error of prediction. So it's a bit of a problem with assumptions, but still, given this picture, I would not worry about it very much. Another question that is very commonly asked: how many people do you need in order to conduct a regression model, to conduct regression analysis? Well, there is no simple answer to this question. Because it depends on basically how strong are your effects, how strong are your regression coefficients, and how correlated are your predictors. And this is something that is not so easy to model. So there are some rules of thumb that people commonly use. To test the overall model, you need to have at least 50 people plus 8 multiplied by the number of predictors. So if you have 2 predictors, you need 66 people in your sample. But to test the importance of individual predictors, to test the beta coefficients, you need 104 individuals plus the number of predictors in your model. So with two variables, in order to test the effects of these variables, you need to have 106 individuals in your sample. And whichever the larger, that rule you should apply. However, this is not universal. So if your effects are very strong, smaller sample might be fine. And if your effects are not so strong, even larger sample is no guarantee that you'll discover them. So you can use in principle G-power to estimate power, but then again, because there is so much uncertainty concerning the associations between your predictors, it's not so easy. When you have your predictors, in SPSS, you can also test for multicollinearity. The first sign of multicollinearity are very strong correlations between your predictors. And if your predictors correlate at 0.90 or more, they are definitely redundant. So you either need to remove one of them, or average them, or add them together and use just a single variable. For example, instead of using two subscales from a questionnaire, which measure almost the same thing and they are very strongly correlated, it makes sense to use just a total score, add them up. If the correlations are around 0.70, it is possible to use these variables in regression, but still you need to be aware that your statistical power might go down, and ideally the predictors should be almost uncorrelated. And you can also use special statistics to evaluate the presence of multicollinearity, to evaluate the presence of redundant variables. In SPSS, we have a special statistic which is called tolerance. And tolerance is 1 minus squared multiple correlation. Squared multiple correlation is basically the variance that is shared by each predictor with all other predictors. And the rule of thumb that is proposed by Barbara Tabachnik and Linda Fiddle is that if your tolerance value goes below 0.30, it suggests strongly that this variable probably is redundant. Maybe you need to exclude it, even if it does not correlate with anything else very strongly, but given the combination of all other predictors, it appears to be redundant. And another statistic which serves the same purpose is called variance inflation factor, but it's basically an inverse of tolerance. So if variance inflation factor is very large, like 4 or above, also this suggests possible multicollinearity, but normally just one of them is enough because they give the same information. One very important thing that we need to remember about regression is that the importance of each individual predictor will depend on what other predictors are there in the model. If this predictor that you're interested in is the only one that captures some specific aspect of your dependent variable, then it will probably appear as important one. But if you have two predictors that both kind of capture the same aspect of your dependent variable and that compete for the same portion of the shared variance pi, then maybe neither of them will emerge as significant. And as a result, you will have a problem with your regression model. So an optimal set of predictors is the smallest set of reliable variables and variables that cover comprehensively all aspects of your dependent variable, that cover the whole range of possible predictors, and that don't correlate strongly with one another. And measurement error might also have some effects on your outcome variable, on the results of your regression model, but I'm not even going to go into that. So just a few words about different types of regression. The simple multiple regression that we have explored so far is a situation when all predictors are entered into the model at once. And sometimes it is really what we want, but sometimes if we have too many predictors, it becomes a bit of a mess. This model becomes too difficult to comprehend. That's why sometimes we use a different type of regression, or basically not a different type, but a combination of analysis, which is called hierarchical or sequential multiple regression. It's a situation when we specify the order of entering our predictors. So we enter predictors in portions. And basically we compare alternative regression models with and without each portion of predictors. And this is good to test some substantive hypotheses. For example, does adding an additional variable contribute more to prediction? And this is the kind of regression that we use very often in research. The third type of regression is called stepwise or statistical regression. And it's a situation when SPSS basically tries to build a regression model automatically based on the correlations of predictors with your dependent variable. So there is, for example, forward regression when SPSS takes the most strongly correlated predictor, includes it into the model, then takes the remaining second one, and it includes additional predictors until R-square stops growing. Or backward regression, it starts with all predictors included, and then it throws them out one by one until R-square starts falling substantially. So the goal is to arrive at the smallest possible number of predictors that capture the largest possible proportion of dependent variable variance. However, this approach sounds very nice, and some people are very excited about it, like, oh, SPSS will build a regression model for me, it will choose my predictors for me. Unfortunately, this approach is not good at all for research purposes, because as you well know, the estimates of all correlation coefficients and of all regression coefficients have a very substantial sample variance. In different samples, the same correlation, that is the same in the general population, in different samples it will have very different values, and sometimes it might not even be significant. So SPSS basically takes the data from your sample and it uses this data to choose some predictors. As a result, in two different samples from the same population, you will get two different regression models with two different sets of predictors. And people who review research papers are well aware of this. They know that statistical regression is very much dependent on chance. That's why it's not a good idea to use it in research. In machine learning, maybe, but there are also special approaches to optimize this, like lasso regression, etc. But we're not going to discuss them. So just a couple of tips to conclude our theoretical discussion of regression. When you choose your predictors, think well about them. Your set of predictors should be based on theory. They should all be relevant to your dependent variable. This set of predictors should be comprehensive. It should capture all the important factors that are essential. Of course, it's not always possible to do it in research, but at least we should try. And our set of predictors should not be redundant. There should not be variables that are very strongly correlated, and there should not be variables that are measuring the same thing. So if you have 3 different questionnaires for anxiety, for example, it's better to just collapse them into a single dimension, a single factor, and then use it in regression. Statistical regression is best not to use it in research. And of course, when you publish the results of your regression, normally the 2 pieces of information that you're supposed to publish is R-squared and beta coefficients. In social sciences, B unstandardized coefficients usually make no sense. So after making this theoretical introduction, let's proceed to a little bit more advanced stuff.